A user in Paris asks for your site, and Route 53 sends them to Ireland instead of Frankfurt, even though Frankfurt is closer. That's not a bug. It's one of 6 routing policies doing exactly what you told it to. But pick the wrong policy for a compliance requirement, and that same behavior quietly breaks the law. You're watching Stack Lessons. This is Cloud Architect Path, Episode 20. By the end of this video, you'll be able to match geolocation, geoproximity, and latency routing to 3 fundamentally different questions about where traffic should go, and understand why picking the wrong one can quietly break compliance or performance. These 3 policies sound alike, and knowing the distinction is what separates a routing decision that works from one that fails under pressure. That distinction also matters on the Solutions Architect Associate exam. In Episode 19, we mapped out the disaster recovery spectrum for Megacorp, Backup and Restore, Pilot Light, Warm Standby, and Multi-Site Active, all ranked by recovery time and recovery point. We landed on Pilot Light for the Frankfurt scenario. Now here's the piece we didn't cover. When the primary region actually goes dark, what mechanism flips traffic to the standby? That mechanism lives in DNS, and it's exactly what we're building today. 5 terms will carry us through this whole video. A routing policy is simply the rule Route 53 uses to decide which answer to give for a query. An alias record maps a domain straight to an Amazon Web Services resource, resolved inside Route 53 and free of charge. The zone apex is the naked root of your domain, example.com, with no www in front. A health check is an automated probe that tests whether an endpoint is actually alive. And bias is a dial, unique to geoproximity, that stretches or shrinks how far a region reaches for traffic. Most people think of DNS as a phone book. You ask for a name, you get back an address. Route 53 is far more than that. It's a programmable traffic director. For the same name, it can hand different users different answers based on where they are, how fast a region responds, or whether an endpoint is even alive. That's the shift you need to make. The name is fixed, but the answer is a decision. One query comes in, and Route 53 has 8 ways to answer it. Simple routing points at a single resource. Weighted splits traffic by percentage. Latency picks the fastest region. Failover handles active-passive disaster recovery. Then geography splits into 2 policies people constantly confuse: geolocation by country and geoproximity with a bias dial. Multivalue answer returns up to 8 healthy records at once. And the 8th policy, IP-based routing, directs traffic based on the site or block the request originates from. We'll take them one at a time, and by the end you'll match each to a keyword instantly. Let's start with the default, simple routing. It points a name at a single resource. No special logic at all. You can list several IP addresses in one record, and Route 53 returns them in random order for the client to pick from. Here's the catch that matters. Simple routing supports no health checks. Route 53 has 0 visibility into whether an endpoint is alive. So if one of those servers goes down, Route 53 keeps handing out its address, and clients keep connecting to a dead machine until a human notices. Think of it like a restaurant listed in the phone book with one address. Everyone gets sent there, whether the place is open or the door is locked. You show up, the door won't budge, and you stand there until you give up. Route 53 never called ahead to check. That's simple routing, no awareness of health. Ever. Weighted routing lets several records share one name, each carrying a weight from 0 to 255. The math is simple. A record's traffic share is its own weight divided by the sum of all the weights. This is how you run A/B tests. Canary releases and blue-green migrations without ever changing the DNS name. Picture testing a new checkout service. The old one at weight 95, the new one at weight 5. Only 5% of users hit the new system. Watch it for a week, then shift to 50/50, then to 100/0. That's a zero downtime migration, all through waits. A wait of 0 has two distinct behaviors depending on context. If you set one record to 0 while the others stay positive, that record gets no traffic, a clean retirement mechanism for an endpoint you want to drain. But if every record in the group is set to 0, Route 53 does not black hole your traffic. It distributes it equally across all of them. That all zeros behavior is a deliberate safety net designed to prevent a misconfiguration from taking your entire site offline. Quick checkpoint before we move on. Simple routing means one resource with no health checks, so a dead server still gets traffic. Weighted routing gives you a proportional split for Canary releases and A/B tests, driven by the relative weights. Next up are the policies that route by performance and by geography, and that's where the real architectural decisions live. Latency-based routing sends each query to the Amazon Web Services region with the lowest measured network latency for that resolver. And notice the word measured. That latency data is historical, collected over weeks from Amazon Web Services edge locations. It's not a live speed test. The consequence catches a lot of architects. The geographically closest region is not guaranteed to be the fastest. When a scenario says performance, or lowest latency, or fastest response, this is your answer. Here's the fact that makes this real. A user in London can get routed to Virginia, over 5,000 miles away, if the historical data shows Virginia responding faster than any European region. Transatlantic fiber capacity, peering agreements, and internet congestion sometimes make the longer path the quicker one. Think of it like a GPS that sends you to a farther store because the roads there are clear. Latency is about the network, not the map. It's worth knowing where latency routing stops and global accelerator begins. Route 53 makes a DNS level decision per resolver using historical latency data, and traffic enters the Amazon Web Services backbone at the target region. Global Accelerator uses Anycast IP addresses to pull traffic onto the backbone at the edge closest to the user, which gives more consistent, real-time latency. So for general regional performance where DNS-level historical data is sufficient, latency routing is fine and cost-effective. For truly latency-sensitive, real-time workloads, where you need active edge redirection and a consistent performance guarantee, Global Accelerator is the stronger choice. Now the pair everyone mixes up, and the reason this episode exists. Geolocation asks one scenario, where is the user? Geoproximity asks a different one, where is the resource, and how far should its reach extend? One is a strict rule based on the user's location. The other routes to the nearest resource but gives you a dial to bend the boundary. Keep those two scenarios separate and you'll never confuse them again. Geolocation routes by where the DNS query originates, continent, country, or US state, and the most specific match wins. This is the compliance policy. Data residency, content localization, distribution rights. If a scenario says EU personal data must stay in the EU, geolocation is how you enforce it by sending European queries only to a European region. One critical caveat, you must create a default record. Without one, a query from a location you didn't map gets no answer at all. The user simply can't reach you. The Route 53 documentation puts it plainly. Geolocation routing lets you choose the resources that serve traffic based on the geographic location of your users, and you can use it to restrict distribution of content only to the locations where you hold distribution rights. Notice the two ideas baked in there, user location and restriction. Those are exactly the words that tell you geolocation, not latency, is the answer. Geoproximity takes both the user's location and the resource's location into account and routes to the nearest resource. What makes it unique is the bias dial. A positive bias, from 1 to 99, expands a region's reach and pulls in more traffic. A negative bias shrinks it. And one update worth flagging, since January 2024, Geoproximity is available as a standalone record policy. You no longer need the traffic flow editor to use it. Older Steady Materials still claims you do, so that's an outdated fact to watch for. The formula is worth seeing. Biased distance equals actual distance times 1 minus bias over 100. So a bias of plus 50 makes a resource appear half as far away as it really is, and that pulls in traffic from a much wider area. Picture each region with a gravitational field. A positive bias increases its gravity and pulls users from farther out. A negative bias weakens it and pushes them toward neighbors. One word of caution: near dense boundary areas, even a small bias change can swing a lot of traffic, so adjust it in small increments. Here's the analogy that locks it in. Geolocation is a border checkpoint. Your passport says Germany, so you go through door A, deterministic, rule-based, driven by your declared location. The keywords are compliance, country, residency, and language. Geoproximity is a taxi dispatcher. It sends you the nearest available cab, but it can also pull extra cabs toward a busy area using a bias dial. The keywords there are shift traffic, bias, and resource location. Match the keyword, and the policy chooses itself. Let's lock in the 3 we just covered. Latency sends users to the fastest measured region, which is not always the closest. Geolocation strictly routes by the user's country, and it's your compliance tool. Geoproximity routes to the nearest resource, but lets you tune the boundary with a bias dial. Now let's see how health checks turn all of this from name resolution into a genuine resilience tool. Failover routing is the answer to the question we left open in episode 19. You designate one record as primary and one as secondary, the classic active-passive pattern. A health check watches the primary, and the moment it fails, DNS responses automatically switch to the secondary. When the primary recovers, Route 53 fails back on its own. Think of it like a backup generator. Utility power runs everything until it cuts out. The generator kicks in automatically, then hands control back when the grid returns. This is how warm standby actually gets wired into DNS. Failover is not instant, and that matters for your recovery time planning. The math is straightforward. The health check interval times the failure threshold, plus the DNS time to live. With a 10-second fast health check, 3 failures to confirm a problem, and a 60-second time to live, your worst-case failover lands around 90 seconds. That's the floor. Route 53 can't flip traffic faster than clients requery DNS, so bake that 90-second window into your recovery objectives. There's a classic cheap disaster recovery pattern built on failover routing. Your primary record points at an application load balancer backed by EC2, with a health check watching it. Your secondary points at an S3 static website. Think of S3 as a massive cloud file store, serving a simple site under maintenance page. When the primary health check fails, Route 53 automatically flips all traffic to that S3 page. You keep the site reachable during an outage, and the standby costs almost nothing to run. One detail: only the primary record needs a health check. The secondary doesn't require one. Multivalue answer routing returns up to 8 healthy records per query, each with its own health check. The key advantage over simple routing is that unhealthy endpoints get filtered out before the client ever sees them. And there's a safety behavior worth knowing. If every record is unhealthy, Route 53 doesn't return an empty answer. It returns up to 8 unhealthy ones, so the client at least has something to try. But be clear on what this is not. It is explicitly not a load balancer. No session affinity, no connection draining, no SSL termination. It's client-side random selection, nothing more. The documentation says it in one sentence. Multi-value answer routing lets you check the health of each resource, so Route 53 returns only values for healthy ones, and then, plainly, it's not a substitute for a load balancer. Picture a concierge who hands you 8 restaurant recommendations, but only one she's personally called to confirm are open. She filters the closed ones out. She just doesn't seat you or manage your table. That's the load balancer's job. People call multi-value simple routing with health checks, but the real difference goes deeper than that. Simple routing uses one record holding multiple values, with no health checks. So dead endpoints stay in the answer, and the client picks blindly. Multi-value uses multiple records, each with a single value and its own health check. So unhealthy records get filtered out and the client picks from a verified list. So when a scenario asks for health-checked multiple endpoints without a load balancer, that's multi-value answer. Now let's solve a problem that has existed since DNS was standardized. The zone apex is your naked domain, example.com, with no www in front. 2 records must store at that apex, the SOA and the NS records. And the DNS specification, RFC 1034, forbids a CNAME from coexisting with any other record at the same node. So a CNAME simply cannot exist at example.com. That's not an Amazon Web Services limitation. It's a rule baked into DPass for over 30 years. Which raises the question, how do you point a naked domain at an Amazon Web Services resource? ALIA records are the answer, and the documentation is explicit. Unlike a CNAME record, you can create an alias record at the top node of a DNS namespace, the zone apex. You can't create a CNAME for example.com, but you can create an alias record for it. ALIA records work because they're internal to Route 53. They get resolved inside the service and returned as ordinary address records, so they never conflict with the SOA and NS records the way a CNAME would. Let's put them side by side. An alias record works at the zone apex, is free for queries to Amazon Web Services resources, and automatically tracks target IP changes, so if your load balancer's underlying address shifts as it scales, Route 53 follows it. It inherits the target's time to live, and it only points to Amazon Web Services resources. A CNAME works on subdomains only, never the apex. It's charged per query, does not track IP changes, but it supports a custom time to live and can point to any host name, including non-Amazon Web Services targets. So for an external partner's domain, CNAME is your only choice. ALIA queries to Amazon Web Services resources are completely free. But a CNAME that redirects to another record inside the same Route 53 hosted zone is billed as 2 queries, one for the CNAME lookup, one for the target address record. At scale, that difference is real money. So if you're pointing at a load balancer or CloudFront distribution, replace CNAMEs with alias records to cut DNS query costs. Route 53 gives you 3 kinds of health check. Endpoint checks directly probe an IP or domain over HTTP, HTTPS, or TCP. Calculated checks combine several child checks with and or logic and a configurable threshold, so you can express whether a whole service is healthy. And CloudWatch alarm checks report healthy whenever a linked alarm is in the OK state. That third type exists for a specific reason, and it's the detail on screen in yellow. Route 53 health checkers run outside any VPC, so they can't reach a private resource directly. Route 53's health checkers run outside any VPC and cannot reach private resources directly. They operate at the Route 53 edge, outside your network boundary entirely. So for any private endpoint, you need to create a CloudWatch alarm inside the VPC to report the health metric. Route 53 then reads that alarm state as its health signal. Think of it like a store manager texting status updates to someone who can't get past the entrance. The alarm is the only channel Route 53 has into your private network. Step back and notice that health checks are the engine underneath everything. Failover switches to the secondary when the primary check fails. Multivalue filters unhealthy records right out of the answer. Weighted can suppress a record that fails its check. And this gives you a clean mental model for disaster recovery. Active-passive means failover routing with one primary and one secondary. Active means any other policy. Weighted, latency, geolocation, multivalue, with health checks on all the records, so every healthy one takes traffic at once. Here's the map that answers most of these scenarios. Lowest latency or performance means latency-based routing. User country, compliance, or residency means geolocation. Shift traffic with a bias or route by resource location means geoproximity. Active-passive, primary and secondary, or disaster recovery means failover. A/B testing, Canary, or a percentage split means weighted. Up to 8 healthy endpoints with no load balancer means multi-value answer, and anytime you see zone apex or a naked domain, the answer is an alias record. Learn that table, and the routing questions collapse into keyword matching. Now let's test how well it's stuck with a quick 5-question quiz. Let's put your knowledge to the test. Question 1. A global media company wants each user's DNS query directed to the Amazon Web Services region that gives the best network performance, minimizing buffering during video playback. Which routing policy fits? Is it A, geolocation routing, B, latency-based routing, C, geoproximity routing, or D, simple routing? Run the keyword rule before you answer. This one is B, latency-based routing. The phrase best network performance is the tell. Latency routing sends each query to the region with the lowest measured latency for that resolver. Remember, that's not always the closest region on the map. Question 2. A company is gradually migrating traffic from a Virginia data center to Oregon. They want to shift more traffic toward Oregon over several months by expanding its effective reach without changing any DNS name. Which policy supports this? A, geoproximity routing with a bias value. B, geolocation routing by US state. C, weighted routing at 50/50. Or D, latency-based routing. Think about which one has a dial to bend the boundary. The right call here is A, geoproximity with a bias value. The word shift traffic and expanding its reach point straight at the bias dial, which only geoproximity has. Geolocation is a strict country or state rule with no way to gradually stretch a region's catchment area. Question 3. A startup needs the naked domain example.com to resolve to an application load balancer whose underlying IP addresses change as it scales. What should they configure? A CNAME record at example.com pointing to the load balancer. B, an address type alias record at example.com pointing to the load balancer. C, a simple address record with the load balancer's current IPs. Or D, a CNAME with a low custom time to live. Lock in your answer before I give it away. It has to be B, and here's why. That naked domain is the zone apex, and CNAMEs are forbidden there by the DNS specification, so options A and D are both illegal. A hard-coded address record would break the moment the load balancer's IPs shift. The alias record works at the apex, tracks those IP changes automatically, and it's free for Amazon Web Services resource queries. Question 4. A bank runs its transaction API in one region as primary with a warm standby in another. On a primary failure, DNS should automatically shift to the standby and fail back on recovery. Which configuration is correct? A, weighted routing with equal weights. B, multi-value answer routing with both regions healthy. C, failover routing with a health check on the primary record. Or D, failover routing with health checks on both primary and secondary. Got your pick? Let's see. The answer is C. Active passive disaster recovery is failover routing, and the subtle point is where the health check goes. Only the primary record needs one. That makes D wrong. Checking both isn't a correctness requirement, and it's a distractor designed to look thorough. Last question. A team lists all 6 of their API instance IPs in a single simple routing record. When one instance fails, users still get routed to it. What's the correct fix to filter out unhealthy endpoints without adding a load balancer? A. Switch to multi-value answer routing with a health check per record. B. Add a health check to the existing simple routing record. C. Switch to weighted routing with equal weights. Or D. Enable evaluate target health on this simple record. Pause here if you want more time. If you said A, well done. The trap is option B. Simple routing supports no health checks at all, so you can't just bolt one on. Multi-value answer routing uses one record per resource, each with its own health check, and filters the unhealthy ones out of the response. That's client-side load balancing without an actual load balancer. And that completes Route 53 routing policies and health checks. If this helped you build real understanding, subscribe so the rest of the Cloud Architect path finds you. I read every comment, so tell me what stuck and what was still fuzzy. Got an exam you'd like a course on? Drop it below. And any ideas to sharpen the pace or the visuals? I'm all ears. See you in the next one.